Welcome to today's video, which covers power series. So this is titled a review of power series. The first part of this video is theoretically review something that you probably saw in BC, such things as power series, radius of convergence, looking at the sum of two power series. And then the second half of the video is going to be new, and that's where we're going to be solving differential equations, but we're going to be looking for a solution in the form of a power series. So let's just start right off the bat with some review. So first of all, let's remember what a power series is. A power series is an infinite series of this form, and this is called a power series that is centered at A. So for example, we might have the series from n equals 1 to infinity. So sometimes it's going to be 0, sometimes it's going to be 1, and maybe we have negative 1 to the power n plus 1 over n squared times x to the n. So this example is a power series centered at 0. So next thing to talk about is convergence. So we say that a power series converges at x if the limit as m approaches infinity of the power series from n equals 1 to m of c to the n x minus a to the n exists. So recall that for a specific x, the power series is going to be a series of constants. So then we say the interval of convergence is the set of all values, all x values, for which the series converges. So we are going to look at some examples of this, but we're going to get through the background first, and then we'll look at some examples where we actually put everything together. So talking about radius of convergence. For this power series, there are going to be three possibilities. First possibility is that the series only converges at x equals a, in which case our radius is 0. And all power series are going to converge at A. Other possibility is that our series converges for all x, satisfying the absolute value of x subtract a is less than r, where the radius is greater than 0. Or last option is that the series converges for all x, in which case our radius is infinity. So at this point you might be thinking, do we need to remember all of those convergence tests? No, we don't need to remember all the convergence tests. We're going to look at this one example and then move on. So this example 1, we are going to determine the radius of convergence for that power series that we are given. So what we're going to do is we are going to use the ratio test. So let's do a quick review of the ratio test, and then we'll actually use it. So we are going to define L to be the limit as n approaches infinity of a to the n plus 1 over a to the n, the absolute value of all of that, for our series that is adding up those a of n's. So if our L is less than 1, then our power series is convergent. If L is greater than 1, then our power series is divergent. And if L equals 1, then the test is inconclusive. Okay, so looking at our example, L is going to be the limit as n approaches infinity. In the numerator, I'm going to have x plus 1 to the power n plus 1 over n plus 1, 2 to the n plus 1. And then I'm going to have x plus 1 to the n over n, 2 to the n, and it's the absolute value of all of that. So this is what I'm going to simplify. So what I can do is I'm going to rewrite this as the product of the two fractions. So I have the x plus 1 to the n plus 1 over n plus 1, 2 to the n plus 1. And then I have n, 2 to the n over x plus 1 to the n. Okay, so doing a little bit of simplifying here. This is the limit as n approaches infinity. Okay, so what I'm going to have is I'm going to have this n plus 1 in the denominator. And then this 2 to the n plus 1 and the 2 to the n is going to leave me with a 2. In the numerator I have n, and I have an x plus 1. Okay, well our limit is only affected by n, so this x plus 1 and this 2 I can bring out. So this becomes the absolute value of x plus 1 over 2 times the limit as n approaches infinity of the limit of n over n plus 1. Now I don't need those absolute value bars because n is going from 1 to infinity, so n is going to be positive. So our L then, right, so this is just 1, our L is the absolute value of x plus 1 over 2. Okay, it appears that I have not given you enough room, so you might have to add another page so that we can keep going. Sorry about that. Okay, so now we know where all of this took us, is we know that our series converges when L is less than 1. So what that gives us then is that absolute value of x plus 1 over 2 has to be less than 1, which gives us absolute value of x plus 1 is less than 2. So what that brings us to then is that x is between -3 and 1. Okay, so this is 4 wide, which means our radius of convergence is 2. And then our interval of convergence is at -3 to 1. We're going to need to check the endpoints though. So we're going to keep going for a little bit and then we'll return back to this interval of convergence to check the endpoints. Okay, so next thing to talk about is absolute convergence. So we say that a series converges absolutely if the sum from n equals 0 to infinity of the absolute value of c to the n x minus a to the n also converges. And so, quick note, power series converges absolutely within its interval of convergence, but we need to test the endpoints, like we said with the previous example. So our interval of convergence, that r, is the limit as n goes to infinity, we already saw this, of c to the n over c to the n plus 1. Okay, so looking back to this example number 1, if we use this idea above, our radius then is going to be the limit as n approaches infinity. In the numerator, c of the n, well, so I don't need that x, is 1 over n, 2 to the n, and then I have 1 over n plus 1, 2 to the n plus 1. And if I simplify that, it's going to give me the limit as n approaches infinity of n plus 1, 2 to the n plus 1, over n, 2 to the n, which becomes the limit as n approaches infinity. If I clean things up, I have n plus 1 over n times 2. So I get a radius of 2, which we already knew. What I want to go back to, though, is this interval of convergence. So what we got before is we got our interval to be that -3 to 1. But we need to test the endpoints. And so that's what I want to do, is test the endpoints. So what we're going to do is we're going to go back to this power series, and we're going to start with 1. So if we plug 1 in, we're going to get the sum from n equals 1 to infinity of 2 to the n over n, 2 to the n, which is just the power series from n equals 1 to infinity of 1 over n. And so you just need to remember that one. You need to remember that that power series diverges. Then if we do x equals -3, we're going to have the sum from n equals 1 to infinity of -2 to the n over n2 to the n. So simplifying that, that becomes the series from n equals 1 to infinity of -1 to the n over n. And this one, if we remember, converges conditionally. So if we were looking for our interval of convergence then, for example number 1, that interval would be from -3 to 1. Okay, so that was our review of convergence and radius of convergence and interval of convergence. Next, we're going to go on and we're going to be looking at combining power series. So just a quick reminder is that a power series represents a function. Right, so if we take our power series and we expand it, that would be c to the 0, add c1 times x minus a, add c2 x minus a quantity squared, and so on and so forth. And so what we're going to be doing is we might be finding the derivative or the integral. And if you want to find the derivative or an integral of a power series, all you're doing is you're going term by term. And of course we can add and subtract power series as well. So let's see an example of this in example number 2. We are going to write x squared multiplied by this power series as a series whose generic term involves the power x to the r add n. Okay, so what I'm going to start by doing is multiplying this x squared in, so it's going to affect the power on this x. So that'll become the sum from n equals 0 to infinity of r add n, a to the n, x to the r add n add 1. Well, we want it to just be r add n, not r add n add 1. So what I would suggest is maybe we just write out the first few terms. So if we substitute in n equals 0, we're going to get r add 0, a to the 0, x to the r add 1. Then if we substitute in n equals 1, we're going to get r add 1, a to the 1, x to the r add 1 add 1, or really r add 2. And then let's do one more. If we substitute in n equals 2, we're going to get r add 2, a 2, x to the r add 3. Okay, so now we need to figure out, this is going to be sum, I'm going to have something, I'm going to have a, and I'm going to have x to the power r add n. And I'm going from n equals something to infinity. Okay, so I'm going to notice from green, my first power needs to be an r add 1. So that tells me that n has to start at 1. Okay, when I do that, I need a of 0. So this can't be a of n, right? Because that would be a of 1. So it's going to need to be a of n subtract 1. And then again, I'm going to need r add 0. So instead of r add n, I'm going to have to subtract 1 again. Okay, so we know if we substitute n equals 1 in, that'll check out. Now check out, if we put in n equals 2, are we going to end up with this term right here? Well, r add 1, okay, so I'm going to have r add 2, subtract 1, which gives me r add 1. I get my a of 1. And then do I get r add 2? Well, r add 2, yes I do. So this is that power series. Okay, let's look at a few other examples. So on the next page, it says, find the first 4 terms of the power series in x for e to the x cosine x. So of course we're going to have to remember the Maclaurin series for these two. So e to the x is 1, add x squared over 2 factorial, add x to the 3rd over 3 factorial, so on and so forth. So that's going to be the series from n equals 0 to infinity of x to the n over n factorial. Okay, cosine x then is 1 subtract x squared over 2 factorial, add x to the 4th over 4 factorial, so on and so forth. And so that is the series from n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. Okay, so if we're looking at e to the x times cosine of x, what we're doing is we're multiplying out those terms. So I'm going to rewrite them so that I can multiply them easier. So I have 1, add x squared over 2, add x to the third over 6, add x to the fourth over 24, so on and so forth. And then my cosine x is 1 subtract x squared over 2, add x to the fourth over 24, so on and so forth. Okay, so 1 multiplied by 1 will give me 1. The only way that I can get an x is if I have x times 1. Then I'm going to need to figure out all the ways that I can get x squared. Well, I can get x squared if I have this x squared times 1, or this x squared times 1. So that's a 1/2 subtract 1/2. Okay, well then, how can I get my x to the third? X to the third, I can have x to the third times 1. Or I can have x times x squared. So that'll be 1/6 subtract 1/2. So then x to the fourth. Well, I have x to the fourth times 1. I have x to the fourth times 1. And then I have x squared times x squared. So that is 1 over 24, another 1 over 24, but this time we're subtracting 1/4. And then there's more after that. So if I go to simplify this, this will be 1 add x, that x squared term is 0. So we're going to subtract x to the third over 3, and then we're going to subtract x to the fourth over 6. And then there's more after that. But that is the first 4 terms. And so all we did was systematically go through each term. Okay, so we have one more example that we're going to take a look at before we actually jump into the differential equations part of this. And so we are writing this summation as one series. Now I'm going to tell you there is a small typo. This should be n equals 0, not n equals 1. Okay, so there's 2 things that we're going to need. First need is that we need the indices to be the same on both summations. Which now with our change is not the case. We have n equals 1 and we have n equals 0. Then we also need x to start with the same power. And you'll see what I mean by that in a minute. And so what I'm going to do is I'm going to start by just recopying what we have above. So n equals 1 to infinity of 2n cn x to the n minus 1. Add the sum from n equals 0 to infinity of 6 cn x to the n plus 1. Okay, so if I plug in n equals 0, this starts with x to the 0. If I plug in n equals 0, this starts with x to the first. So that's a problem. We need x to start with the same power. This first power series has an extra term of x to the 0 that we don't want. So what I'm going to do is I'm going to pull that out. If I substitute in n equals 1, I have 2 times 1 times c1 x to the 0. Now, since I pulled out this n equals 1, the first term, my summation now starts from n equals 2. And that second series, I didn't do anything to, so it just stays the same. Okay, so now we can verify if we plug in 2, we have x to the first. If we plug in 0, we have x to the first. So what we've done is our second need is accomplished. Now we're on to the first one. And so here's what you do with that first one, that first need. We're going to introduce a new variable k, and I'm going to make it this power. So I'm going to make k be my power n minus 1, which means that n is equal to k plus 1. Now, I'm going to use k again for this second summation. If you don't like k, if that's uncomfortable, choose something else. So if you don't want to use k, choose something else. So maybe let's use j instead. my j is going to be equal to n plus 1, which means that my n is j subtract 1. Okay, so where does that leave us then? This term we still have, so we still have 2c1. Now I'm solving. If n is 2, that means that k is starting at 1 to infinity. I then have 2 instead of n, that gets replaced by k plus 1. I have c to the k plus 1 and x to the k. Then I have the summation. If n was 0, that's going to make j equals 1 to infinity. I have 6c instead of k. It's going to be to the j subtract 1, x to the j. Well, now, it doesn't really matter if I'm using k or j, right? They're both just, they're just variables, so it doesn't matter. I just need to pick one variable. So this j is really, we're going to think of it k. We're going to make everything in terms of k. So we're really thinking of that as the summation from k equals 1 to infinity of 6c to the k minus 1, x to the k. And so now, finally what I can do is this summation becomes, I still have that 2c of 1, but now both summations have the same indices, so that's going to be the summation from k equals 1 to infinity. And then I have 2k plus 1, c of the k plus 1. And then I also have this 6c of the k subtract 1 times x to the k. So this is my final answer. Now, quick note. If you want to check, you can write out a few terms. So substitute in k equals 1, k equals 2, k equals 3. Go back to your initial summation here and make sure that you end up with the same terms. Okay, so before we go on to the differential equations part of this, there's a few other quick things we need to write down. So above in example number 3, we looked at e to the x and cosine x. You're also going to need the Maclaurin series for sine of x. So the first few terms are x cubed over 3 factorial, add x to the 5th over 5 factorial, so on and so forth. And so that becomes the series from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And just to recall some vocabulary, remember that a Maclaurin series, so the 3 series that we've written down, are just a Taylor series where x is 0. So again, writing down just a little bit, your Taylor series, you wrote some function f of x as a sum from n equals 0 to infinity of the nth derivative evaluated at a over n factorial times x minus a to the n. So the first few terms, we would get f of a, add f prime of a, multiplied by x minus a, add f double prime of a times 2 factorial x minus a squared, so on and so forth. But when we say it's Maclaurin, we specifically choose x to be 0. So I know this was a lot. What we're going to do now is we're going to take a look at solving differential equations, and we're going to get a solution in the form of a power series, and we're going to kind of put a lot of these skills together. Don't get too frustrated or nervous yet. Let's look at some examples so you know what the expectations are going to be. Okay, so this is the new stuff. We're going to be looking at power series solutions of differential equations. So let's consider this first differential equation. If we were to solve this, hopefully we would notice right off the bat that the equation is separable. So we have dy dx is equal to 2xy. If we separate, we have dy over y is equal to 2x dx, and we're going to integrate, which would give us natural log of y is equal to x squared add c. Solving for y, we would get y to be e to the power x squared add c, which tells us that y equals e to the x squared is one solution. So, using a Maclaurin series, that same solution can be expressed as y is equal to the sum from n equals 0 to infinity of x to the 2n over n factorial. So what we're going to be doing today is, instead of finding this solution, y equals e to the x squared, we're going to be finding the power series solution. Okay, so what we're going to do is, in example number 5, we are going to solve that same differential equation we had above, so we already know what our solution is going to be, but we're going to solve it using series rather than separation. Before we start writing, I'm going to warn you that this is a pretty long process and it's very detail oriented. So it's very easy to make a small mistake that will set you up for failure for the rest of the problem. So we're going to have to be very cognizant and careful. Okay, so let's get started. First thing is, we will assume that a solution does in fact exist. In the form y is equal to the power series from n equals 0 to infinity of cn x to the n. Okay, so if we start with that, y is equal to the sum from n equals 0 to infinity of cn x to the n. Looking at our differential equation, we see that we're going to need dy dx. So we're going to need to take a derivative. So if I'm taking the derivative with respect to x, n would come down, and then I have cn x to the n minus 1. Now what we notice, though, is that n equals 0 gives us 0. So really, we're going to start that summation at n equals 1. Because that is the first non-zero term. So then what we're going to do is we're going to go back to that differential equation, and we're going to substitute in these two power series that we have. So that becomes then the summation from n equals 1 to infinity of n c to the n x to the n minus 1, subtract 2x times the summation from n equals 0 to infinity c to the n x to the n, and all of that is equal to 0. This is where that last example comes into play now. So thinking back to our two needs, we need our indices to be the same, and we need these to start with the same power. Well, before we do that, let's deal with this 2x, which I'm going to multiply in. So what this becomes then, first summation stays the same. That second summation becomes 2c to the n x to the n plus 1. So the first thing that we did, if you remember, is make sure they start with the same power of x. So if we substitute in n equals 1, we have x to the 0. If we substitute in n equals 0, we have x to the first. So that's a problem. If we remember, what we did is we pulled out that x to the 0 term. So substituting in n equals 1, I have 1 times c1 x to the 0. Because I took out that n equals 1 term, I now start at n equals 2. And everything else is going to stay the same. Okay, so now we should verify. If we substitute in n equals 2, we have x to the first. If we substitute in n equals 0, we also have x to the first. So that's good. Our first need is met. Now, second need is that our indices are the same, which they are not in this case. So this is where we introduced our next variable. I'm going to make k be the n minus 1. Now, if you remember, what we did next is we used j, but that eventually got turned back to k. So what we can do is we can just use k again. If you feel more comfortable using j and then going back to k, you certainly can do that. Okay, so where this takes us then. So I have c1 plus, if n is equal to 2, that means that k would start at 1 to infinity. And then this also tells me that n is the same as k plus 1. So this will give me k plus 1, c to the k plus 1, x to the k. Second summation, if I substitute in n equals 0, again, I'm going from k equals 1 to infinity. I also know that n is equal to k subtract 1. So this will be 2 c to the k subtract 1, x to the k is equal to 0. Okay, so now my indices are the same, which means I can combine these two power series. So this becomes c1, add the summation from k equals 1 to infinity of k plus 1, c to the k plus 1, subtract 2 c to the k minus 1, all of that times x to the k is equal to 0. Okay, so this is the same as our differential equation dy dx, subtract 2xy is equal to 0. So that is the same as our differential equation. Again, I didn't give you a ton of room, so if you write as big as me, you might need to get a new page. Okay, so where we're at. In order for all of this to equal 0, two things need to be true. Firstly, c1 would need to equal 0. And secondly, this constant, so that k plus 1 c to the k plus 1, subtract 2 c to the k minus 1, would have to equal 0 for all of the k terms starting at 1. So what we're going to do is we are going to solve this for c k plus 1. And if we do, it gives us 2c to the k subtract 1 over k plus 1. And so this you've seen before. This is called a recurrence relation. So what we're going to do is we're going to find some of those terms. So because we're starting with k equals 1, I'm going to substitute in k equals 1. So that gives me c2 is equal to 2c0 over 2, which is just c0. If I substitute in k equals 2, this gives me c3 is equal to 2c1 over 3. Well, c1 from above we know is 0, so this just gives me 0. If I substitute in k equals 3, I get c4 is equal to 2c2 over 4. Well, c2 we have above, right? c2 is the same as c0, so replacing that, I get 1/2 c0. And we're going to do a few more to see if we can find a pattern. If we substitute in k equals 4, we get c5 is equal to 2c3 over 5. Well, c3 above we know is 0, so this term is just 0. If I substitute in k equals 5, that will give me c6 is equal to 2c4 over 6. Well, c4 I have here, which is 1/2 c0. So that gives me 1/6 c0. And I'm going to do two more. K equals 6 will give me c7 is equal to 2c5 over 7. Well, c5 we know is 0, so this is really 0. And the last one that I'm going to do is k equals 7, so that will give me c8 is equal to 2c6 over 8. Well, that c6 is what we have above here. So that is really 1/4 multiplied by 1/6 c sub 0, which is 1 over 24 c sub 0. Okay, so the question is, where does this leave us? Where this leaves us is that our solution, like we defined before, is y equals the power series from n equals 0 to infinity of cn x to the n. Okay, so that is c0 plus c1x plus c2x squared, so on and so forth. Well, we've found those terms then. We're using all of these terms that we found above. This, so on and so forth. So that gives us c0, add our c1 is 0, our c2, we found that above is right here, so that's c0 x squared, and then we have 0, and then we have 1/2 c0 x to the 4th, so that comes from here. And then we have 1/6 c0 x to the 6th, and then we have 1 over 24 c0 x to the 8th, so on and so forth. And at this point, I'm going to give us a new page. So we notice all of those terms that we had have a c0 in them, so I factor that out. That is 1, add x squared, add 1/2 x to the 4th, add 1/6 x to the 6th, so on and so forth. Well, 1/2 I know is 1 over 2 factorial. 1/6 is 1 over 3 factorial. And if you remember, we had a 1 over 24, which is 1 over 4 factorial. So then this is c0. Well, this power series, we know. That is the power series from n equals 0 to infinity of x to the 2n over n factorial. This is our general solution. Now, you should remember from when we solved this by separation, we know that our general solution is c e to the x squared. So you might be asking, how do I go from this power series to this solution that's in a little bit of a friendlier format? Well, what we can do is we can rewrite this power series from n equals 0 to infinity. I can write this as 1 over n factorial times x squared to the n over 1. Well, this now hopefully you recognize as e to the x squared times c. Now, what we're going to be doing is we'll be stopping here. I'm not expecting us every time to take a power series solution and get it back to this function format. Stopping at the power series is what we want. We are going to do one more example because I know that this was a long process, but we have one quick note or quick review real quick for you. And that is, what is the power series solution, or not solution, what is the power series for cosine of 1/3 x? I want to make sure we know how to do that. Well, we know cosine of x is this power series from n equals 0 to infinity of -1 to the n, x to the 2n over 2n factorial. All you do for cosine of 1/3 x is you take 1/3 of x and you replace it for x. So cosine of 1/3 x would be n equals 0 to infinity of -1 to the n, 1/3 x to the 2n over 2n factorial. So hopefully that makes sense on the previous example, how this x squared just became x squared to the n. Okay, so I know this is a long process and it's a bit of a doozy, so we are going to do one more example, and then in the next section we'll continue with this process. Okay, quick review. We already did that on the previous page, so I'm just going to move on. Last example, find a series solution of the equation y double prime, add y is equal to 0. Okay, so our y, like we defined before, is the solution from n equals 0 to infinity of Cn x to the n. We're going to need a second derivative, so I'm going to have to differentiate a few times. So I get n equals 0 to infinity of n Cn x to the n minus 1. And we said before that that first term is 0, so we're instead going to start the summation at 1. So then the second derivative, I'm going to have n times n minus 1, c to the n, x to the n minus 2. Again, if you substitute in 1, our first term is 0, so we're going to start the summation at 2. Okay, so now at this point, we're going to go back to our differential equation. So our y double prime add y is equal to 0, substituting in those terms that we have above. So we have the summation from n equals 2 to infinity of n minus 1, Cn x to the n minus 2, add the summation from n equals 1 to infinity, n equals 0 to infinity of Cn x to the n, and all of that is equal to 0. At this point, you might want to pause the video. I would suggest that you pause the video and see, can you get this as a single summation? So we've done 2 examples so far where we've done that. So just take 5 minutes and see, can you get this as one summation? And then when you're ready, come back. Okay, so if I plug in n equals 2, this starts with x to the 0. If I plug in n equals 0, this also starts with x to the 0, which is good. That means one of our 2 needs is met. Problem now being we have different indices. So here, I'm going to let k be equal to n minus 2. Here, k is equal to n, which means I don't have to do anything with that second summation. The first summation is the one that I'm going to change. So my n then is equal to k plus 2. So I'm going to start from k equals. If I substitute 2 in for n, my k will start from 0. And this n is the same as k plus 2. And then I have k plus 1, c of the k plus 2, x to the k. That second summation stays the same, except I'm going to use k instead of n. Okay, so now at this point, my indices are the same, so that's great. So this becomes the summation from k equals 0 to infinity of k plus 2, k plus 1, c of the k plus 2, add c of the k, x to the k equals 0. Okay, so hopefully if you tried that, that's the point that you got to. Now, this is only going to be 0 if the coefficient is 0. So we get k add 2, k add 1, c of the k plus 2, add c of the k is equal to 0. And that is for k equals 0, 1, 2, so on and so forth. So that gives us our recurrence relation. If we solve for c of k plus 2, that would give us negative c of k over k add 2, k add 1. That is our recurrence relation. And remember, this applies for k is 0 and above. Okay, so the next thing that we did is we used this recurrence relation to come up with a few of the terms. So I'm giving myself a lot of room, but if I start with k equals 0, what that gives me then is that c2 is equal to negative c0 over 2 times 1. And I'm just going to leave it as 2 times 1 to see if I can come up with a pattern moving on. If I substitute in k equals 1, I'm going to get c3 is equal to negative c1 over 3 times 2. So if we notice, this is 2 factorial, 3 factorial. If I substitute in k equals 2, I'm going to get c4 is equal to negative c2 over 4 times 3. So then if we remember, we have this c2 above that we're going to use. So this is the same as positive c0 over 4 factorial. So then if I use k equals 3, I'm going to get c5 is equal to negative c3 over 5 times 4. C3 we have above though, so that's the same as positive C1 over 5 factorial. And if we do one or two more, if I substitute in k equals 4, I'm going to get C6 is equal to negative C4 over 6 times 5. And again, choose that C4 from above. So that's the same as negative C0 over 6 factorial. Okay, so then if we put this together, if we remember, general solution is going to be C0, add C1x, add C2x squared, add C3x to the third, so on and so forth. From these terms that we found above, we should notice that some are in terms of C0, and then we're going to have some terms that are in terms of C1. And so when I write my solution, what I'm going to do is I'm going to make sure that I write those separately. So I'm going to continue over here. So what I end up with is if I have those C0 terms, that's 1 subtract x squared over 2 factorial, add x to the fourth over 4 factorial, so on and so forth. And then those C1 terms are x subtract x third over 3 factorial, add x to the fifth over 5 factorial, so on and so forth. So this one is a little bit different than what we saw above because we actually have two solutions in this case. So if I rewrite this first power series, so that is the sum, if I use an n equals 0 to infinity, of negative 1 to the n over 2n factorial, x to the 2n, and then I have C1, the sum from n equals 0 to infinity, of negative 1 to the n over 2n plus 1 factorial, x to the 2n plus 1. And those should look familiar. And so finally, where we're going is that we have two solutions. So what we have written above is the general solution, but we want our two separate solutions. So our y1 is that c naught times the sum from n equals 0 to infinity of negative 1 to the n over 2n factorial x to the 2n. And then our second term, so that should really be y1 of x, is the sum from n equals 0 to infinity, negative 1 to the n, 2n add 1 factorial, x to the 2n add 1. So these are our two solutions. And like I said, they probably look familiar to you. So we can express these differently. We can express y1, that is the power series for cosine of x, and that y2 is the power series for sine of x. Okay, and then lastly, we just have this quick note that we need to write down. We don't need this now, but we're going to need this in the next section. So a function f is analytic at a point A if it can be represented by a power series in x subtract a with a positive radius of convergence. Okay, so what that means is next section we're still going to be doing power series. So we're going to have a very similar idea or process in the next section. So thank you for sticking with me through this long video. I will see you when you get to class.